video is on how to do the calculations for the ideal gas constant lab. So this is my data table. These numbers are completely made up and they're obviously wrong because if your temperature is 0 degrees Celsius, then that's freezing. So unless you're doing this outside in January, these aren't going to be your numbers, so don't copy these numbers. But we're assuming that I already did the experiment and I already got all these numbers. And so how do we do all this crazy looking stuff in data table 2? So first of all, you have to calculate the concentration of H2O2. And in your lab, I think they give you 3% concentration, but I'm going to do a calculation of 5%. So 5% concentration of H2O2 simply just means you have 5 grams of H2O2 for every 100 grams of water. So we have to go from grams over grams to moles over liters for concentration, because our concentration is going to be for molarity, which is moles over liters. So the first thing I'm going to do, I'm going to convert this 100 grams of water to liters of water. So I'm going to have 100 grams of water. And my conversion factor in 1 liter is going to be 1,000 grams. And that's going to come out to be 0.01 liters of water. So now we have 5 grams of H2O2 over 0.1 liters. And so we have to go from grams over liters to moles per liter. And so then our next step is to convert from grams to moles. So then what we're going to need to do is, in H2O2, there's going to be 34 grams of H2O2 in 1 mole, and this just comes from the molar mass. Oxygen is going to be 16 times 2, which is 32, plus 2 hydrogen, which is 34 grams. And 1 grams of H2O2 are going to cancel. And we're going to have, for 5%, you guys have 3%, for 5% of H2O2, it's going to be 1.44 molar. So you're going to have to go through and do this concentration with 3 grams over 100 grams. So our next box asks us for moles of H2O2 in each trial. So now that we have moles per liter, so we have 1.44, so we're going to go to moles, 1.44 moles per liter, and we have to go from moles per liter to just moles. So in other words, we got to get rid of this liter. And in the first trial, in trial 1, there was 1 milliliter of H2O2 used. And then of course we have to convert this to liters. So it's going to be in 1 liter, there's 1,000 milliliters. And so my milliliters are going to cancel, my liters are going to cancel, and we're just going to multiply across. And for my first trial, it's going to be 0. It's going to be 0.0014 moles. For trial 1, you'll have to go through and do this again for trial 2 and trial, for the 2 milliliters and the 3 milliliters. And so that takes care of concentration of H2O2, moles of H2O2, and then you have to do moles of O2. Alright, so we have moles of H2O2 here, and then we have to do moles of oxygen. So how do we figure out what our moles of oxygen is? Well, we have to have the balanced equation, which is found in the background. We have our balanced equation here. So it's going to be I have 2H2O2 going to 2H2O plus O2. And for trial 1, if I started out, if I have this many moles of H2O2, then I have to figure out how many moles of oxygen I'm going to get. So, for my balanced equation, it takes 2 moles of H2O2 to get 1 mole of H2O. That's our conversion factor, but we don't start out with 2 moles, we start out with this. So we're just going to have to convert using stoichiometry. Right, and then I put the 2 moles of H2O2 down here. And that with 1 mole of O2. I'm going to multiply across to get, well, pretty much we're just dividing by 2. So that's 0.00072 moles of O2. And then you have to do this for each trial, because you'll have a different number of moles depending on how many milliliters were used in that particular trial. Okay, so our next step, next thing the data table asks for is your delta V in liters. So you're pretty much just taking your milliliters and dividing by 1,000, because there's 1,000 milliliters in 1 liter. Your air temperature and your pressure you're going to get from your phone. And so what is the equation of this? What is this line thing that it's talking about? So what you're going to have to do is you're going to have to go into Excel, and in the background under activity 2, it asks for, in step 7, create a best fit line on your graph. Oh, in step 6, sorry. Using a computer program, create an XY scatter plot of the moles of oxygen versus the volume of gas. So in your Excel, you know, you're going to have A, column B, and you have your cells, right? And so it would be helpful for you to go ahead and label it and say, so you have to do an XY, moles of oxygen, moles of O2, and then you have to do that versus the change in volume. So that's going to be delta V in liters from your table. So these two things come from your table. And so then you're going to have your numbers from 1 to 8, and your numbers from 1 to 8. And then you're going to have to make a scatter plot. So you're going to go into Excel, you're going to have insert, scatter plot, and there should be a place where it says create a line of best fit. So there should be an option that says trend line, right? And so you want to check show trend line, or line, it might say line of best fit. You want to display that, and you want to display the R squared value. And I want to stress that there are 2 R values here. R squared talks about the accuracy of your data. The closer it is to 1, the better. Now your R, just regular R, is the ideal gas constant. So these are 2 different R's. So your R squared just tells you about the accuracy of your data. And your R that you calculate from the equation that you're going to get from your line of best fit is the ideal gas constant, and that's what you're looking for. Okay, so once you get your equation, right, when you get your equation, it's going to be in the form of y equals mx plus b. Okay, so what you're going to do is you're going to take your equation and we're going to analyze it. B should equal 0 because it asks you to set your y-intercept to 0 in step 7. So B should equal 0 according to step 7. Okay, so X equals the number of moles and Y equals the volume. And M, of course, is your slope, and M equals R, the gas constant R, times your temperature over your pressure. Okay, so you want to find R. That's what you're looking for. So whatever you have for your slope, we're going to use that to find R. So if this is what R equals, we need to isolate R, and pretty much when you rearrange your equation, MP over T is going to equal your slope times your pressure over temperature is going to equal, excuse me, R. Okay, so I'm going to give you a really quick example problem. Okay, at standard temperature and pressure, okay, my equation is y equals 26.125x. So we're going to use this slope to figure out what R is. So R equals my slope times temperature over pressure, pressure over temperature, excuse me. So R equals 26.125 times, at standard temperature and pressure, it's going to be 1 atm over 275 Kelvin, 73 Kelvin. Equals 0.096. That is the calculated ideal gas constant value, my average value from all my trials. This is obviously very wrong because the R value is 0.821. So for my percent error, which is the last thing you have to calculate, it's going to be experimental minus the true value divided by the true value times 100. So for my very terrible experiment, it'd be 0.098 minus 0.821 divided by 0.821 times 100 to make it a percentage, and that's about 90% error. So don't copy my numbers. But that is how you calculate, that's how you use the line from your Excel document to get your slope and then your R value and your percent error.